Hey, today we're going to do a deeper dive into a case study, the Therac 25. I'm hoping this lesson highlights some issues with technology that can be correlated to technology today. Engineers in the fulfillment of their professional duties shall hold paramount the safety, health, and welfare of the public, perform services only in areas of their competence, issue public statements only in an objective and truthful manner, act for each employer or client as faithful agents or trustees, avoid deceptive acts, conduct themselves honorably, responsibly, ethically, and lawfully so as to enhance the honor, reputation, and usefulness of the profession. So we're going to talk about the Therac 25. The Therac 25 was a special device used for radiation therapy. It was first built in the 80s, somewhere in the mid-80s. It was built by the Atomic Energy of Canada Limited Company. There had been two working previous versions of the Therac 6 and the Therac 20. The Therac 6 was good for dermal cancers, so cancers right on top of your skin, and the Therac 20 was good for deep-seated tumors. So previously, if a hospital wanted to be able to treat both of these, it needed two machines. In this case, the Therac 25 was the merger of these two technologies. This is the first computer-operated medical radiation machine. That means the software 100% controls the system. This includes safety. It was compact and computer-operated, so it was relatively easy to use. Because there was a high level of confidence in the software, they did not do the full battery of testing. All right, so what I want you to do is, and this should be in the video description, but I want you to watch the video from the beginning to about 2.5 minutes, and then I want you to respond to each of these questions. So if you were in class, I would just walk around and discuss, but you're watching from home. We've seen the first signs that something went wrong, but we do not yet know how the device was designed. Before we continue, let's examine the technology being trusted in this system. Okay, so if you're watching from home, watch the other video from about 2.5 minutes to 4 minutes, and answer these questions. We now understand the machine's core design choice. Next, we'll see how those choices lead to the first confirmed failures. All right, so if you're watching from home, you should now watch the video from minute 4 to minute 7.25. At this point, multiple patients have now been injured, but the company's response is unchanged. Review these questions and answer them. All right. So if you're watching from home, this should be about 7 minutes, 15 seconds to 9 minutes and 30 seconds. We're beginning to see a pattern of errors. The next section reveals how a specific software defect caused repeated overdoses. Yeah, so just answer those questions. All right, so if you're watching from home, this should be minute 9 and 30 seconds to minute 13 and 50 seconds. Now that the software issue has been reproduced, we'll move into the regulatory and organizational responses. Even after a corrective action plan, a deeper flaw remained. This next portion shows the consequences of untested code paths. All right, so we've reached the end, or no, we haven't, sorry. We've reached the final fatality. The remaining segments cover organizational outcomes and lessons. we've now seen the entire sequence of events. Let's connect these points back to engineering ethics. Again, just read the questions, answer them based off of what you just saw. In the end, the FDA notified AECL that they've lost their license in the US, meaning they couldn't sell hardware to US hospitals. The existing hardware was forbidden to use. Hospitals demanded refunds under warranty. The FDA notifies the public that Therac 25 has caused 6 radiation-based deaths. So try looking at this from the FDA's point of view. What else are they supposed to do at this point? Therac has more or less shown, AECL has more or less shown they're not going to do shit unless they're forced to. Why else, or what else could the FDA do here, right? And if you're relying on the FDA to do their job, what else would you expect them to do? Now, the FDA orders an independent company to review the Therac 25, and sure enough, the independent review identified plenty of bugs, and they immediately replicated the error once they knew where the bugs were. Therac refused to do this to themselves. Why? I don't know. They had a conflict of interest in the review. Self-review is expected in a real-world application. However, in a real-world application, measures need to be put in place to remove bias. At the company I work for, I audit our own tasking. Now, the truth is, when I do it, I have a lot of trouble removing my bias. But one thing that the company I work for has observed and tolerates is that my bias is never in favor of us. It's always more critical of what the actual auditor will do. So it's tolerated. However, you might not be in that situation. You might not have that luxury. So if you know the people you're working with are too nice or too easy to deal with or are very critical of criticism, you have to find a way to work around it. As a company, you are both expected to create material, create design, create products, but you're also expected to review the product's risk and issues related to reputation, cost, and how long things take. If you do not do this up front, other people are going to make you do it down the line, and that, I promise you, will always be more expensive, either in the form of lawsuits or regulators coming in. And unfortunately, one reality that engineers need to live with is small errors can kill people. That's why, a long time ago, my dad was an engineer, there was no partial credit. If you put a minus sign where it wasn't supposed to be, the response by the professor was, in a real-world application, that will kill somebody. And the truth is that's still the case. So you have to do the self-check up front. And if you can't be trusted to do the self-check, they're going to get somebody else to do it for you, and it's not going to be cheap. AECL in this case was blind to their own errors, and this happens a lot. This isn't a unique engineering thing. This is everybody does this to some extent. There are some families that can't see their own errors. Same thing's happening with AECL. So I want to talk about why I brought up AECL, or more accurately, the Therac 25. So this case is famous, not just because of technology and that it was unique. It's famous because it shows how everyday engineering decisions, when combined, can result in severe consequences. So in this case, we have a device that emits radiation. That's one set of technologies. We have software that controls the technology. We have a mechanical moving device. These are all different groups of people, different engineers working on the design. And so no one of them had any intent to hurt anybody. In fact, they were all trying to help cancer patients, right? Um, but for whatever reason, the environment they were in um, put them in a spot where they couldn't prevent failures. Students often assume disasters result from bad actors or extraordinary incompetence. That's not what happened here. They were probably very competent. They just couldn't see their own errors. Ordinary people doing what they believe is reasonable can still create very unsafe outcomes. This is why we study these events, to understand how assumptions, communication failures, and organizational culture shapes the safety of every system we design. The lessons apply no matter what field of engineering you enter. The Therac 25 incident show what happens when unusual reports are dismissed because they appear improbable, or they just say something you don't like. When something does not match your expectation, you must investigate. This is non-negotiable. You have to do your due diligence. You have to go check. Ambiguous warnings are themselves system failures. Pressure to meet deadlines can quietly steer decisions away from safety, often without explicit acknowledgement. And assume no assumption is safe unless verified through evidence. Confidence is never a substitute for testing. A phrase you should learn now and use frequently is, "I trust you, but I need verification." You have an ethical obligation here. The NSPE code is not just a formality. It is a framework intended to prevent outcomes like those in the Therac 25 case. Engineers must be willing to pause or challenge processes when safety is uncertain. Many of the failures in this case occurred because individuals assumed someone else had already done the necessary checks. Even seemingly minor decisions, such as how error codes are displayed or how input is validated, can deeply affect user behavior and system outcomes. Ethics is not about reacting after harm occurs, it's about identifying risks before they are reached. I want you to keep in mind that AECL, because they refuse to do a self-check, because they refuse to fix their errors, there are now a handful of legal codes based around what they did. It's not just radiation devices anymore. It's any automated medical system now has to go through a whole litany of tests because of this. People died, so the FDA made a whole ton of rules. And the thing is, AECL wasn't breaking that many laws, but because it's a gap in the system, the FDA had to do something. And the FDA themselves didn't fully understand what was going on. So a lot of the laws they made don't make a lot of sense, and they're hard to comply with, which inherently makes the technology and the products more expensive. You don't want that. As a consumer and as an engineer, you don't want that. So you need to do the legwork now to avoid these problems. Learning to do this now will serve you throughout your career. Legacy systems, much like the Therac 25 software, often contain hidden risks due to outdated practices or missing documentation. I saw this every day. I still see this with submarines all of the time. You have to ask, why are we doing things this way? Is this the right way to do it? Or was this just the good enough way you found when you started the process? And you need to be critical about it. Rather than assuming they're correct and optimized, which they rarely are, simply because they worked in the past. Go through it and say, how can this fail? If that failure occurs, what will happen? Will someone get hurt? If the answer is yes, make sure that failure is impossible. Either change the system or change the design. Documenting, which I know it sounds like scut work and it's annoying and nobody likes to do it, documenting decisions helps create continuity and transparency, especially when teams change over time. And importantly, communicating concerns early is one of the strongest defenses against systematic failure. Speaking up is part of your professional duty. You're going to hurt somebody at work. This is not an abstract idea. You're going to do it by accident. And you're going to live with it. You're not going to like living with it. No, you're probably not going to kill somebody. No, you're probably not going to do it on purpose. And for the most part, you'll probably have done everything you thought you could have done to make it better. And you're going to realize that's not good enough. I don't want you to learn the mistakes I've learned the hard way. I want you to learn them now. Every decision, whether it's software, design, analysis, affects people. You want to make sure that that effect is always good. In the case of Therac 25, the victims were patients seeking treatment. They trusted their hospital enormously. But now, do you think those patients and those families genuinely trust the hospital and doctors they were working with? Probably not. And is it really their fault? No, but that doesn't matter. All those kids remember is mom went in okay and she came out either dead or maimed. We're not aware of the technical decisions behind these machines. They trusted that those decisions protected them. They assumed that the hospitals and the doctors and the nurses had already done all that work. And they assumed that the company had done all that work. And the reality is none of that work was done. You need to make sure that everything that was supposed to have happened, all of the testing, all of the legwork, all of the foundational stuff, is done, whether it's your job or not. A lot of times just checking that it was done and saying who did it, who's responsible for it, is enough. You have to do it. I want you to think about what kind of engineer you will be. Not what you want to be, but what you will be. And that you should start trying to be that person now. Your career will place you in situations where the right answer is unclear and where pressure encourages shortcuts. The truth is, you're not going to know that you've made a bad decision, that you've hurt somebody, and that you regret it until days, weeks, months, maybe even years after the fact. And that's a heavy thing to carry. I don't want you running into those situations. In those moments, your values matter as much as your technical skill. Cultures of safety are built by individuals who choose caution, transparency, and integrity, even when it's inconvenient. Cases like the Therac 25 are not just historical examples, they are reminders of the responsibility you carry as an engineer.